thanks for starting recording. Great. Okay, let me just do a quick introduction of our guest today, Professor Liu Zhao from Zhejiang University. It's a great pleasure to have him here today. So Liu Zhao got his PhD program from Institute of Physics of Chinese Academy of Science, and he did his postdoc research at Princeton University, and we have a slight overlap at Princeton, and that is followed by another postdoc position at the Free University of Berlin, and he joined Zhejiang University as a faculty, I think 3 years ago. And his research interest mainly focuses on strongly correlated systems, including fractional quantum Hall effect, fractional Chern insulators, and all other topological phases, and their interaction with disorders and localization. And he also did some research in non-equilibrium dynamics as well. And he's an expert in coming up with a large-scale numerical analysis of these strongly interacting systems. So without further ado, let us welcome Professor Liu Zhao. And Liu Zhao, the floor is yours.
Okay, thank you, Boyan. Thanks for the invitation. So it's my great pleasure to give a talk here. Today I will talk about my recent results on fractional Chern insulators in Moire flatbands. In this project, I collaborate with Professor Emil Burkhaus and his PhD student Ahmed Abu Kamsan at Stockholm University. Okay, my talk has 4 parts. In the first part, I will briefly introduce the continuum, integer, and fractional quantum Hall effect in the 2D electron gas. And in the second part, I will introduce Chern insulators and fractional Chern insulators, including the motivation to search for fractional Chern insulators, and how can we numerically identify fractional Chern insulators in microscopic models, and the existence of lattice-specific fractional Chern insulators and the new competing physics in lattice models. In the third part, I will show you the existence of fractional Chern insulators and their competing physics in graphene-based Moire systems, including the Lovelings fractional Chern insulators in chain number 1 band in twisted bilayer graphene aligned with hexagonal boron nitride, and the lattice-specific fractional Chern insulators in chain number 2 band in twisted double bilayer graphene. And we also observe interaction-induced Fermi liquid-like states in trilayer graphene aligned with hexagonal boron nitride. And finally, I'll give you a summary. Okay, let's start from the quantum Hall effect. Well, we know from high school physics that if we have a thin metal sheet in a magnetic field, we apply a current in the x direction. Then finally, we get voltage in the y direction because of the Lorentz force. We define the Hall resistance as the ratio between the voltage in the y direction and the current in the x direction. Then classical physics predicts that this quantity should be proportional to the magnetic field. This is called the classical Hall effect, first measured by Edwin Hall in 1879. And nowadays, new technologies allow us to check this relation for 2-dimensional electron gases at very low temperature, as low as a few millikelvin, and in very strong magnetic fields, as strong as a 15th of Tesla. And these 2-dimensional electron gases can be prepared as the interface between 2 different semiconductors. Okay, if we measure the Hall resistance as a function of the magnetic field in cold 2D electron gas, this is a typical curve we can get. So at weak magnetic field, we can observe the classical Hall effect, where the Hall resistance is just proportional to the magnetic field. However, if we increase the magnetic field, we can find the deviations of the Hall resistance from the classical prediction. In particular, Hall resistance develops plateaus near integer fillings nu equal to n. For example, here is a plateau near integer filling nu equal to 1. Here is another plateau near nu equal to 2. Here the filling factor is defined as the ratio between the number of electrons n and the number of magnetic flux through the sample n phi. On each of these plateaus, the Hall resistance is precisely quantized at the value h over n e square. Here, h is a Planck constant and e is the electron charge. And this is called the integer quantum Hall effect, first observed by von Klitzing, Doda, and Pepper in 1980, more precisely at 2 a.m. February the 5th, 1980. So they worked really hard. Okay, so how to explain the integer quantum Hall effect? Well, I will show that the integer quantum Hall effect can be understood in, in a non-interacting picture. We don't need to consider the electron-electron interaction. We know for a 2D electron gas in a magnetic field, Landau levels are formed. So this is a single particle Hamiltonian for an electron in a magnetic field. And we know its eigenenergies are quantized into Landau levels at n plus 1/2 h bar omega. Here omega is the cyclotron frequency. And if we don't consider the edge effect or disorder, then each Landau level is exactly flat, which means all single particle states within a Landau level are exactly degenerate. We can show this degeneracy is the same as the number of magnetic flux through the sample. So that's why we define the filling factor as the number of electrons divided by the number of flux. And we can further show that each fully filled Landau level contributes to a quantized Hall conductance or resistance h over e square. And this is related to a topological invariant called chain number. So chain number is equal to 1 for each isolated Landau level. And this relationship between the transport quantity Rxy and the topological invariant chain number was first established by Saulis in 1982. In the explanation of the integer quantum Hall effect, it's very important that the ground state is gapped at the integer filling. Well, we know at the integer filling, the ground state is just the n-filled Landau levels below the Fermi energy, right? So the gap is just the energy spacing between the highest occupied Landau level and the lowest unoccupied Landau level. So it's equal to h bar omega. And this gap gives us a well-defined ground state with a cracked Hall resistance h over n square. And we can further show that if we add disorder in the sample, then disorder can create a localized state within this gap. Then if we tune the filling factor slightly away from the integer filling nu equal to n, the newly added electrons, they occupy localized states, so this Hall conductance doesn't change. Then we have the plateau near integer fillings. So now you can see that the integer quantum Hall effect is just a result of Landau level quantization and the weak Anderson localization in the sample. So a single particle picture works. Okay, however, the integer quantum Hall effect is not the end of the story of the quantum Hall effect. If we further increase the magnetic field, we can observe more plateaus. However, those plateaus do not develop at integer fillings. They develop around near fractional fillings nu equal to f. And for example, here we have 4 plateaus near filling 2/3, 2/5, 1/3, and 2/7. And on each of these plateaus, the Hall resistance is precisely quantized at the value h over f e square. And this is called the fractional quantum Hall effect, which was first observed by Cui, Storm, and Gossard in 1982. So how to explain the fractional quantum Hall effect? Actually, the logic is similar to the integer case. If we have the bulk gap at some proper fractional filling, then we have a well-defined ground state with a cracked Hall resistance h over f e square. Then weak disorder in the sample can also produce localized states within the gap. So if we slightly tune the filling factors away from nu equal to f, then the newly added electrons, they still occupy localized states. So we have a plateau near the filling factor nu equal to f. So now the problem is, the question is how to open a gap at a fractional filling. Well, at integer fillings, it's easy to open a gap because in this case, the bulk gap naturally appears as as a Landau level spacing, as I said before. However, at a fractional filling, for example, 1/3, because all single particle states within this partially filled Landau level are degenerate. So if we don't consider interaction between electrons, we will have a huge degeneracy. For example, if we have 100 non-interacting electrons at 1/3 filling of the lowest Landau level, you can calculate the degeneracy, which is roughly 10 to the 81, roughly the same as the number of atoms in the universe. So it must be the interaction that opens a bulk gap and produces the fractional Korn-Hall effect. And because of this strongly interacting nature, it's really difficult to study the fractional Korn-Hall effect. In the past 30 years, people mainly use topological field theory, trial wave functions, and numerical simulations in microscopic models such as exact dilatation and density matrix renormalization group to theoretically study the fractional Korn-Hall effect. Of course, all theoretical results should be compared with experimental observations. Now I would like to introduce more about trial wave function. I will show you an example, the Lovelings wave function. Well, here, trial wave function means we can first guess what is the ground state at a specific filling factor. Then we make some predictions based on this trial wave function. Then we compare with numerical simulations and experimental observations. Okay, now I show you the Lovelings brilliant ansatz wave function. Okay, let's consider a 2D electron gas on a disk geometry. Then the lowest Landau level single particle states can be written in this form. Here, Z is a position of an electron, M is an integer starting from 0, and L is a magnetic length. So at filling factor nu equal to 1, when the lowest Landau level is fully filled, the many-body wave function is just a simple Slater determinant spanned by these single particle states, which can be written in this elegant form. Now we want to ask what is the filling, what is the ground state at filling factor 1/3? Well, Lovelings made a slight modification in this nu equal to 1 wave function. He just changed the power of Zi minus Zj from 1 to 3. And this is his ansatz wave function for 1/3 filling. And this modification can indeed changes the filling factor from nu equal to 1 to nu equal to 1/3. And later people found that this wave function matches both numerical simulations and experiments. So now we believe that the 1/3 fractional Korn-Hall effect is indeed described by this Lovelings ansatz wave function. And people also found that this Lovelings state has some amazing properties. The first property is its degeneracy. Its degeneracy is equal to 3 to the power of G on a genus G surface. So it only depends on the genus of the surface. So this degeneracy is called topological degeneracy. For example, if we put the Lovelings state on a sphere surface, because the genus is equal to 0 in this case, then the degeneracy is 1. However, if we put it on, for example, the surface of a coffee cup or a torus, then we have threefold degeneracy. The second amazing property is that the quasi-particle excitations in the Lovelings state is fractionalized. Here, fractionalized means the quasi-particles carry fractional charge and they obey fractional statistics. The topological degeneracy and fractionalized quasi-particles are defining features of intrinsic topological order, which was proposed by Xiaogang Wen in 1990. So we know fractional Korn-Hall states, including the Lovelings state, they carry intrinsic topological order. Okay, I would like to talk more about fractionalization. Here, we still consider the Lovelings state as an example. For example, we want to create one quasi-hole in the Lovelings state. What we need to do is just to multiply this factor, Zi minus W, to the Lovelings wave function. In this way, you can see that all particles cannot be located at the position W, otherwise this wave function is 0. So if we want to create 3 quasi-holes at the same place, W, then the wave function is like this. If you look at this wave function, you can see that we can just replace the position W by an electron, another Z, to create the Loveling state with one more electron. So in this sense, three quasi-holes can be compensated by a single electron, which means each quasi-hole carries charge minus E over square. Here, E is the electron charge. So each quasi-hole carries a fractional charge, and this fractional charge has been observed by short noise measurement in experiments. Moreover, the quasi-particles in the Loveling states, they also obey fractional statistics. If we exchange two quasi-holes, for example, in the Loveling state, you can show that finally we get an extra phase e to the I 2 pi over 3 in the final state. And this extra phase is not +1 for boson and not -1 for fermions. So the quasi-holes or quasi-particles in the Loveling states, they are neither bosons or nor fermions, and we call them anyons. And the Loveling quasi-particles, they are abelian anyons, because if we change two Loveling quasi-particles, we get an extra phase in the final state. However, we also have non-abelian anyons in other fractional quantum Hall states. Non-abelian anyons means if we exchange two quasi-particles, the final state can be related to the initial state by a non-trivial, non-linear transformation. And in this case, if we have multiple quasi-particles, the order of exchanging them is important. For example, if we have three quasi-particles, the final state by first changing 2 and 3 and then 1 and 2 is different from the final state obtained by first changing exchanging 1 and 2 and 2 and 3. And this is why we call them non-abelian. And these non-abelian quasi-particles are conjectured for other fractional quantum Hall states, like the state at 5/2 and 12/5. And these non-abelian quasi-particles are supported by this conjecture is supported by quasi-particle interference and thermoconductance measurement in experiments. And these non-abelian quasi-particles in fractional quantum Hall states could be used as resources of topological quantum computation, which was proposed by Kitaev in 1997. Okay, so now I finished the first part. Now let's go to the second part, Chern insulators and fractional Chern insulators. Okay, we have seen that the quantum Hall effect in 2D electron gas in a strong magnetic field has many amazing properties. So one natural question is, are continuum 2D electron gas and strong magnetic fields necessary for realizing the fractional quantum Hall effect? Actually, for the integer quantum Hall effect, we already knew the answer is no 30 years ago. This is because in 2D lattices, if we have a lattice 2D with broken time reversal symmetry and a fully filled isolated block band with chain number C, according to the linear response theory, it contributes a quantized Hall conductance equal to E squared over H times the chain number C. And this is exactly the same as the integer quantum Hall effect in the continuum. So this is called the lattice integer quantum Hall effect, and it's also called Chern insulator. Here, Chern means the transport depends on the chain number C, and insulator means we must have a fully filled isolated band, so the Fermi energy is within the band gap. And magnetic fields are not required in this scenario because we don't need a magnetic field to create a block band with chain number C, right? And in 1988, Duncan Haldane, he proposed a model for Chern insulator, and this is called the Haldane model. So Haldane model is just a spinning graphene with real nearest neighbor hopping plus complex next nearest neighbor hopping. This complex next nearest neighbor hopping can be imagined as a result of some local magnetic field However, the directions of adjacent local magnetic fields are opposite, so the net magnetic field is still 0. And this Haldane model, it has two energy bands carrying chain number +1 and -1 respectively. So if the Fermi energy is within the band gap, the lower band is completely filled, then we have the integer quantum Hall effect on the lattice. Okay, and from the Haldane model, we can also see the notable differences between Chern insulator and conventional integer quantum Hall effect. The first difference is that in Chern insulator, in general, the block bands are dispersive, so they have a finite bandwidth. However, in conventional integer quantum effect, we know Landau levels are exactly flat if we don't consider edge effect and disorder. The second difference is that in Chern insulators, the topological bands, they in general have non-uniform barrier curvature or other band geometry quantities. However, in conventional integer quantum effect, we know Landau levels, their barrier curvature is uniform, corresponding to the uniform external magnetic field. And the third difference is that in Chern insulators, we can have block bands with higher chain number larger than 1. However, in the conventional integer quantum effect, each Landau level can only carry a chain number equal to 1. For example, in Haldane model, if we further add the nearest neighbor hopping, we can have a chain number 2 band. According to the bulk edge correspondence, if we have a chain number 2 band, then we have 2 chiral edge modes along the boundary of the sample. Okay, regarding experiments, there have been a lot of experiments which realize integer or Chern insulators. The first experimental observation was made in March 2013. And in the title, they use quantum anomalous Hall effect. Actually, this is another name for Chern insulator. Here, anomalous means we don't have an external magnetic field. And then in some cold atom systems, Haldane model was also realized. And recently, we also observe high chain number Chern insulators in experiments. Okay, so now we have seen that the integer quantum effect can be realized in lattice models at 0 magnetic field. So a natural question is, can we find lattice analogs of the fractional quantum effect? You may wonder why we need to look for fractional quantum effect in lattice models. After all, we already have it in continuum 2D electron gas, right? So in my opinion, I think the motivation is based on 2 points. The first one is the dream of realizing fractional quantum effect more easily. We know the conventional fractional quantum effect in 2D electron gas, it requires very strong magnetic fields and very low temperature. However, in lattices, we wish to relax these strong requirements. First, we wish to realize the fractional quantum effect in lattices at 0 or at least a much weaker magnetic field. Well, we already realized the integer quantum effect in lattices at 0 magnetic field. Well, the second hope is in lattices, we can realize fractional quantum effect at much higher temperature. Well, because the lattice spacing is 10 to 100 times smaller than the magnetic length in the continuum, so if we estimate the energy gap by the Coulomb interaction, naively, we would expect that in lattices, the energy gap is 10 to 100 times larger than in the continuum. So if we can realize the fractional quantum effect in lattices, it could survive to much higher temperature than in the continuum. Well, the second motivation is we may find lattice-specific fractional quantum effect. And this is because the block bands are notably different from Landau levels, as I said before. For example, block bands, they have non-zero band dispersion, they have non-uniform barrier curvature, and they can carry a high chain number. So if we can find lattice-specific states, then they can broaden our understanding of the fractional quantum Hall effect. Okay, so based on these two motivations, people have started to look for fractional quantum Hall effect in lattices, or dubbed as fractional Chern insulator. So where to search for fractional Chern insulator? Well, we know in the continuum fractional quantum Hall effect, we first need an exactly flat Landau level with chain number 1. And then we partially fill the Landau level by interacting particles at proper filling factor. We may find the fractional quantum effect. So in lattices we can follow the same logic. So we need to look for lattice models in which we have a flat block band with non-zero chain number, and then if we partially fill this flat topological band by interacting particles, then at proper filling factors, maybe we can find the lattice fractional quantum Hall effect of fractional Chern insulators. And indeed, people have found solid numerical evidence that fractional Chern insulators can indeed exist in various lattice models. The first three papers appeared at the same time on PRL in 2011. Okay, given a lattice model, how can we know the ground state is a fractional Chern insulator? People often use numerical simulations in microscopic models, and this is the most general tight-bending Hamiltonian for a lattice model. The first term is a hopping term, is a single particle hopping term, and the second term is the interaction. Here I choose the Hubbard-like interaction, and then to remove the edge effect, we can put the lattice on the torus geometry. Namely, we consider periodic boundary conditions. In this case, the band filling factor can be defined as the number of particles in the flat band divided by the number of unit cells in the lattice, because the number of unit cells is the same as the number of single particle states in a single band, right? And then we often assume that the low energy difference is constrained in the partially filled topological flat band. Then we can project this Hamiltonian to that partially filled flat band. After the projection, the projected Hamiltonian takes this form. The first term is a band dispersion. Here, gamma k Dagger creates a particle with momentum k in that partially filled band, and Ek is a band dispersion. Here, k should be in the first Brownian zoom. And the second term is interaction. The projected two-body interaction. Here, the matrix element of Vk, it contains information of the band eigenvector. And after this projection, we can gain a much larger numerical efficiency because we reduce the Hilbert space dimension. Okay, then we can use many numerical techniques to diagonalize this projected interaction. For example, we can use hexagonalization or DMRG. And then we have many things to check to confirm the ground state is a fractional Chern insulator. Well, I think the first thing to check is the ground state degeneracy on the torus. And this is a typical energy spectrum for fermionic 1/3 fractional Chern insulator in a chain number equal to 1 band. You can see that the ground state is always approximately 3-fold degenerate for different system sizes, 6, 10, or 12 electrons. And this degeneracy becomes better with the increasing of the system sizes. And there is always a gap separating the ground state manifold from highly excited states. And this energy gap doesn't decay quickly with the increasing of the system size, and it probably survives in the thermodynamic limit. So this means in this case, we probably have a 3-fold topological degeneracy, which is a fingerprint of fractional Chern insulator. Of course, we often need more diagnosis to confirm the ground state is fractional Chern insulator. For example, we can also check the entanglement spectrum, quasi-Hall statistics, modular matrices, topological entanglement entropy to further confirm the nature of the ground state. Okay, based on numerical simulations in macroscopic models, people have found many fractional translators. For example, in chain number 1 bands, people have found a series of fractional translators, and all of them have conventional fractional quantum states as continuum counterparts. Actually, this is not surprising because each Landau level also carries chain number 1. But we have found something more interesting. As I said before, one notable difference between block band and Landau level is block band can carry high chain number, and we can also find a series of fractional translators in high chain number bands. For example, in one of my paper, I have found fermionic fractional translators at filling 1/2c plus 1 at high chain number bands. Here C is the band chain number, and for bosons, these states exist at filling 1/c plus 1. And we can show that the fractional translators in high chain number bands are lattice specific. They don't have conventional fractional quantum states, even the multi-component states as continuum counterparts. So they are lattice specific. Moreover, we find we can also have lattice specific competing phases of fractional translators on lattices due to the broken of particle symmetry in a chain band. Well, if we consider the flat band limit, then the projected interaction only contains the interaction term. Then we make a particle transformation to switch from the electron picture to the whole picture. In this case, we need to exchange gamma k with gamma k dagger, and then the filling factor of electrons is changed from F to 1 minus F. Then after the particle transformation, the electron interaction is transformed into the hole interaction, which contains two terms. The first term is a hole-hole interaction, and the second term is a single hole dispersion, which depends on the interaction matrix elements. And we can see that this single hole dispersion, because it depends on this interaction matrix element, so it's entirely induced by the electron-electron interaction. In a single Landau level, we can show that this single hole dispersion after the particle hole transformation is a constant due to the magnetic translation symmetry. So this means the fractional quantum effect must appear in pairs at the electron filling F and 1 minus F, because after particle transformation, the Hamiltonian is just changed by a constant. Well, unless the particle symmetry is broken by multi-body interactions or Landau level mixing. However, in a chain band, we can show that this single hole dispersion after the particle transformation, it in general depends on the momentum k. So it's in general dispersive. And this means the particle symmetry is broken in a single chain band, even at the level of projected two-body interactions. And in the whole picture, if this whole dispersion dominates over the whole interaction, then the ground state cannot be a fractional translator. Instead, it must be a Fermi liquid-like state. And indeed, we observe this Fermi liquid-like state driven by the whole dispersion in Moire superlattices. I will show you later. Okay, regarding experiments, there have been several promising proposals to realize fractional translators, for example, by artificial gauge fields in optical lattices or in dipolar spin systems. However, up to now, experimental observations of fractional translators at zero or weak magnetic field are still missing. Well, recently, Moire Superlattices become a new promising platform. There has been one experiment which reports the observation of fractional quantum effect in the bilayer graphene hexagonal boron nitride superlattice. However, in this experiment, they still applied a very strong magnetic field, roughly 30 Tesla, but this definitely means Moire superlattices at zero weak magnetic field are worthy of study. Okay, now let's go to the third part, fractional translators in graphene-based Moire systems. Okay, so what is Moire superlattice? Well, when two periodic lattices lie on top of each other with a relative twist or mismatched lattice constant, they can create a Moire pattern, and this Moire pattern has a special structure on a larger scale than either of the lattice alone. And this periodic pattern forms a larger lattice, and this is called the Moire superlattice. Here, I give you an example of the twisted bilayer graphene. So at the beginning, we have two layers of graphene on top of each other. Then we twist the bottom and top layers by a small angle theta plus and minus theta over 2. Then you can see the formation of the Moire pattern. And this Moire pattern is equivalent to a triangular Moire superlattice. And the lattice constant of this Moire pattern is equal to the graphene constant A0 divided by 2 sine theta over 2. So when theta is small, this Moire pattern is very long periodic. And people find that the band structure of the Moire superlattices is highly tunable. We have many ways to tune the band structure, for example, by changing the twist angle, by applying external fields, or inducing strain, or putting a substrate. Well, there are many ways to tune the band structure in Moire superlattices. And if the active bands near the Fermi energy, they are tuned to be flat, then this system is an ideal platform to study strongly correlated physics, such as superconductor, correlated insulator, and ferromagnetism. And we are especially interested in Moire systems in which the active bands are not only flat, but also topological. Then we can examine whether we can realize fractional Chern insulators when these topological Moire flat bands are partially filled by Coulomb interacting electrons. So to check this possibility, we consider 3 different types of Moire systems. The first one is twisted bilayer graphene aligned with hexagonal boron nitride. And the second one is twisted double bilayer graphene. And the third one is trilayer graphene aligned with boron nitride. Okay. We need to first formulate a single electron model to show the existence of topological flat band in these Moire systems. Well, let me use the twisted bilayer graphene aligned with hexagonal boron nitride as an example. In this case, let's assume, okay, before twisting, the monolayer graphene Boolean zone is spanned by 2 vectors, B1 and B2. Then after rotation, after twisting, the Boolean zones of the 2 layers, they are also rotated by plus and minus theta over 2. Then we can show that the smallest reciprocal lattice vectors are no longer B1 and B2. Instead, they are G1 and G2, which can be related to B1 and B2 by this relation. And then you can see that this G1 and G2, they are very small compared with the original B1 and B2. So this means the monolayer graphene Boolean zone is folded into small Moire Boolean zone. And in this figure, this large hexagonal is the original monolayer graphene Boolean zone, and these small hexagonals, they are Moire Boolean zones. And then for low energy electronic behavior, we can focus on the Moire Boolean zones near the K plus or K minus points of the 2 graphene layers, namely this region and this region. And near the K plus points of the 2 graphene layers, we have the plus valley for twisted bilayer graphene, and near the K minus points of the 2 graphene layers, we have the minus valley for the twisted bilayer graphene. And we can use a continuum model to describe the behavior of electrons in each valley of the twisted bilayer graphene if the Moire period is much longer than the atomic spacing. Okay, here I show you this continuum model. So in this model, first we neglected inter-valley mixing because these 2 valleys are far separated from each other. Then for a specific valley, for example, valley plus and a fixed spin, the continuum model can be written in this form. So here K is near the K+ points of the two layers in this region. And the first two terms, they correspond to the two monolayer graphenes. Here, the small h is a direct Hamiltonian of the single layer graphene rotated by minor set over 2 and set over 2. And psi T and psi B, they are spinors, two component spinors of the top and bottom graphene layers. And the third term corresponds to the tunneling between the two graphene layers. The tunneling matrix element T has this form, and here W0 is a tunneling between AA sets, and W1 is a tunneling between AB sets. And the last term is the effect of the aligned boron nitride, which breaks the C2 symmetry to open a gap at the direct points of the twisted bilayer graphene. And the other value, the value minors, can be related by the time reversal conjugate. Okay, then if we diagonalize this single electron model, we can see that there are indeed topological flat bands in the Moire Superlattices. For example, in this TBG HBN model, we can see that near the charge neutral point, we have two topological bands with chain number +1 and -1. And in twisted double bilayer graphene, if we do similar calculations, we can find near the charge neutral point, we can have higher chain number conduction and valence bands. And in trilayer graphene aligned with boron nitride, the conduction band near the charge neutral point carries chain number 3, and it can be tuned to be very flat. And if these topological bands in Moire superlattices, they are completely filled, in experiments, we have observed Chern insulators. So it's really promising that if these bands are partially filled, we can have fractional Chern insulators. Okay, so now let's consider the partially filled Moire flat band. In this case, the projected interaction can be written in this form. The first term is band dispersion, and the second term is the interaction. Here, K is constrained into in the Moire Boolean zone. And for the interaction, we consider the screened Coulomb interaction between electrons. And here we model the screening by the Yukawa potential. Okay, so here are the numerical results. First, we check the chain number 1 valence band in the twisted bilayer graphene aligned with boron nitride, and we set a filling factor at 1/3. And in this case, we indeed find compelling numerical evidence of the Lovelings fractional Chern insulators. So this is the energy spectrum. We find for different system sizes, for example, 8 and 10 electrons, we always have 3-fold degeneracy for the ground state, and these states are separated from higher states by a finite energy gap. And if we do the finite size scaling of this energy gap, these green dots, we find they probably go to a constant when the system size goes to thermodynamic limit. And here we also make a scaling of the splitting between these three ground states, and we find their splitting decays with the increasing of the system size, so the degeneracy indeed becomes better and better. And here we also check the quasi-hole spectrum, and in this quasi-hole spectrum, we find a gap, and the number of levels below the gap matches the Lovelings prediction. So all of this evidence strongly suggests that the ground state at 1/3 filling in the chain number 1 valence band of twisted bilayer graphene aligned with boron nitride is a Lovelings fractional Chern insulator. And these results are not sensitive to the precise values of model parameters. And we also check the twisted double bilayer graphene. For twisted double bilayer graphene, we can tune the band structure and the topology near the charge neutral point by changing the twist angle theta and applying a vertical voltage U. And we can see that for the conduction band, there are 3 regions. One is chain number equal to 0, and one is chain number equal to 1, and one is chain number equal to 2. In this chain number 1 region, at 1/3 filling, we also find the evidence of Loveling fractional Chern insulators. And more interestingly, in this chain number 2 region, at 1/3 filling, we also find evidence of fractional Chern insulators. You can see that, okay, this is the energy spectrum for 1/3 field conduction band, chain number 2 conduction band of twisted double bilayer graphene. So for different system sizes, 8, 10, and 12 electrons, the ground state is always threefold degenerate, and they're separated by a finite energy gap from highly excited states. And this energy gap is roughly 5 Kelvin, which is much higher than required by the conventional fractional quantum states in 2D electron gas. So this means if we can, this means this fractional Chern insulator can indeed survive up to a much higher temperature. And we also check the particle spectrum of these states. Again, there is a gap, but the number of states below this gap is different from that for the 1/3 Loveling state. So this means what we find here is not a Loveling state, but lattice-specific novel fractional Chern insulators in chain number 2 band without continuum counterpart. Okay, however, we do not always find fractional Chern insulators in Moire flat bands. For example, in the chain number 3 flat band of trilayer graphene aligned with boron nitride, we did not find any evidence of fractional Chern insulators. Why? We found this can be understood in the whole picture after doing a particle transformation. So here, we plot the ground state occupation of electrons in each key point in the Brane zone as a function of the whole dispersion, which emerges after the particle hole transformation of the projected Hamiltonian. For trilayer graphene, chain number 3 band, we found that the Fermi surface-like structure of NK emerges for filling factor higher than 1/3 filling. 1/3 filling is this orange curve. So in this curve, you can see that for some for small minus EHK, the occupation of electrons is close to 1, then it suddenly drops and roughly goes to 0. So this is the Fermi surface-like structure. And this structure becomes more and more better and better if it goes to higher and higher filling factors up to 9/10. And if we decrease the filling factor, we can still see a strong correlation between this NK and the whole dispersion EHK. This means in trilayer graphene chain number 3 flat band, the whole dispersion is always comparable or even dominates over the interaction. So that's why we cannot have fractional Chern insulators at the ground states. For comparison, we also plot the same thing for the chain number 1 band in twisted bilayer graphene boron nitride. And we can see that at small filling factors, the dependence of NK on EHK is much less pronounced. So this NK is more uniform without clear Fermi surface features at small filling factors. And this Fermi surface only occurs at very large filling factor. For example, this 4/5, this pink one. So that means the twisted bilayer graphene is a more suitable platform to realize fractional Chern insulator because the whole dispersion does not dominate over the interaction. And indeed, we observe 1/3 Loveling state here, as I said before. So in trilayer graphene, we believe we observe electron interaction driven Fermi liquid-like states. Okay, so now I come to the summary. So in this talk, first I show you that fractional Chern insulators in topological flat bands provide new chances to realize fractional quantum Hall-like physics, including lattice-specific states with relaxed experimental requirements. And Moire topological flat bands are promising platform to host fractional translators. And there are many interesting future directions. For example, the most natural question is, can we find non-abelian fractional translators or multi-component, for example, spin and valley fractional translators in Moire flat bands? And what is the interplay between band geometry and interaction in Moire systems? And we know most previous studies about fractional translators, they focused on static properties, but what about non-equilibrium dynamics? For example, the quantum quench, or periodic driving, the flochet, or dissipation dynamics of fractional translators. I think these are also interesting to study. And of course, we need to look for the possibility of fractional translators in more materials, not only the graphene-based Moire superlattices. And okay, here is my contact information. And these two papers are the reference papers related to my talk. Okay, thank you very much for your attention.
Okay, thank you very much for the very nice talk. Okay, now we have time for questions. Do we have any questions from the audience? Maybe I can start with one. So yeah, so for the Moire lattice of the TBG, so they have experimentally seen the Chern insulator you mentioned. Yeah. What do you think is the challenge of seeing, for example, the fractional Chern insulator? So from the numerical point of view, when you look at the band is quite flat,
yeah.
But how is the Barry curvature distribution? Is it uniform or not very uniform?
Well, the Barry curvature is not very uniform. Well, in numerics, we see evidence of fractional translators in TBG. However, I think there are indeed some challenges to experimentally see these states. Okay. I think the first one is whether spin and valley are polarized at fractional filling. Here in numerics, I suppose spin and valley are polarized, but this is not guaranteed in experiments.
I see.
And yeah, maybe some disorder and edge effects, who knows, in experiments.
I see. Yeah, maybe just a follow-up question. So for the Chern number equal to 2 bands, I think that's so new stuff from the fractional Chern insulators. So the numerics you show here is you have a Loveling-like state, but the quadrical countings are different from the Loveling. So how different is that from, for example, in second Landau level, right? You also see quadrical countings all messed up, but people still believe it's a Loveling phase. How different is the situation here?
Well, I think in the second Landau level, you still have Chern number 1, right? A single Landau level. So here we have a single Chern number 2. So I think
I'm thinking from, for example, when you characterize a topological phase, you talk about these topological indices. In quantum Hall, we have the Hall conductivity, Hall viscosity, the chiral central charge, and the quadrical counting, right? So if you think in terms from this perspective, what are the topological indices?
So for this state, the Hall conductance should be 2/3 times E square over H, not 1/3.
Oh, I see. Okay. So
so I have calculated the Hall conductance is 2/3, not 1/3.
Because C is equals to 2.
Yeah, right.
Okay, but it's not the for example, the Loveling, anti-Loveling state, etc.
No, I don't think so.
How do we distinguish between the two topological phases? The quadrical counting is one thing that you mentioned probably.
Yeah, and I think another issue is, well, if we have Loveling and an anti-Loveling, probably the number of electrons must be even, right? Because we have two hobbies.
For anti-Loveling, do we have to have even? Yeah, I mean, yeah, if the filling factor is the numerator is 2, then it has to be even number. Yeah.
But in our case, we also find these states for odd numbers.
I see. Okay. I see. Okay. Yeah. Any questions from the audience? I don't want to monopolize here. I think you gave a very good.
Can I ask a question?
Yes, please. Yeah.
Yeah, okay. Thanks for the intuitive explanations. I would like to ask a simple question. Like, as I can see, we have different Chern, we can achieve different Chern numbers in the TDBG. Then is it possible to have any Chern number, I mean, generally in such a system? And how can we tune them in the experiments? Just by adding some long-range interactions between sites, or is there any better ways to do that?
So in TDBG, so here we tune the band topology by changing the twist angle and applying a vertical voltage, and we only find the Chern number 0, 1, 2, 3 regions. We didn't find other regions. But it's indeed possible that we can add longer hopping to achieve higher Chern numbers. Yes, you are right. Yeah.
Oh, I
So
see.
in general, we can add longer and longer hoppings to get higher and higher Chern numbers.
Okay, but it would be harder to achieve in the experiments, I guess.
Right. Yeah.
Okay.
Yeah, that's true.
And also, is there an analytical expression between this angle and the Chern number?
Mm-hmm.
So, like what you have said, we can tune the voltage and the angle to get different Chern numbers. So, is there an analytical expression between them to describe the relationship between them?
I don't know. So here we just
for now, you have to do numerics with a specific, for example, electrical field and the angle to check the Chern number of the band.
Yeah.
So there's no intuitive or analytical way of predicting it without doing numerics, I suppose.
No.
Okay, thank you very much.
Okay. Okay, good. Any other questions?
Yeah.
Yeah, Pinaki, please.
I have a few questions, some of them very naive. Start with, in twisted bilayer graphene, where does the Berry curvature come from?
I think the Berry curvature come from the opening of the gap at the Dirac points, because we also add boron nitride as a substrate, right?
Right.
So that's where the Berry curvature come from. It's the Berry curvature concentrates at the gamma points. I remember.
But there is a spontaneous symmetry breaking of time reversals. So it's very
that's
polarized.
3-2T breaking.
I see.
The interaction driven in some, you have a very polarized state. So the other valley has the opposite Chern number, right? Yeah.
Right.
Oh, okay. And a follow-up question is, this is a continuum model.
Right.
How do you get a higher Chern number? Is it from the discretization of the momentum space? Because normally, as you said, and that's what I also thought, that for Landau level physics, you have only Chern number 1.
Right.
Is it because here, even though we are considering the continual limit, the momentum is still, there is still a Brillouin zone?
Yeah, there's still a Brillouin zone.
Is that what enables higher Chern numbers? I don't even know whether it makes any sense.
Yeah, I think the question is there an analytical way of understanding? Is it because of folding of the Brillouin zones? And
one possibility is the folding of the Brillouin zone, and another possibility is we find this high Chern number bands only in TDBG and tri-layer graphene. So in these two cases, we have many layers of graphene. Then for example, in TDBG, each sheet is is a bilayer graphene. Then we twist them. And so for each state, we already have 2 layers of graphene, and maybe that gives us higher chain number.
Okay, yeah. I was going to come to that. That goes back to user's question also. The higher Chern numbers can also be attained by stacking, right?
Right. By stacking, by adding longer hoppings.
Yeah.
Okay, I see.
And that's why you can go up to C equals 3 for trilayer graphene.
Trilayer graphene. Yeah. So in TBG, we can only reach chain number equal to 1 because in each state we only have a monolayer graphene.
In only one monolayer. In TDBG, you have 2 monolayers, 2 effective monolayers.
Right.
And in trilayer, you have 3 layers.
Right.
Does that mean if you go to 4 layers, you're
Yeah, that's true.
Yeah.
Okay, I see.
Yeah. Okay, thank you.
Welcome.
Okay, maybe I have a follow-up question. So here, you talk about this phase, because in band systems, the difference from the band system and the Landau level problems is that you have 2 things. One is the bandwidth, which is non-zero. The other one is the Berry curvature distribution that is non-uniform. So you mentioned a little bit about the phase transition when the bandwidth is large, then you have a Fermi liquid.
Right.
Okay. Can you talk a little bit more about those phase transitions? Even is there going to be a phase transition when you go from uniform Berry curvature to non-uniform Berry curvature? And is it always going to be transition to a gapless phase, or it can be transition between different gapped phases? Are there studies on these?
So in my work, I find the transition from fractional Chern insulator to gapless Fermi liquid
with the bandwidth. This is by tuning the bandwidth.
Yeah. If I tune the Berry curvature,
I suppose it's hard to tune the Berry curvature easily.
If I tune the Berry curvature, I'm not sure whether we can go to another gapped phase.
Well, we can definitely close the gap by making the Berry curvature very bizarre, right?
Right.
The reason I ask is also I remember there's a paper by Dasama's group. They have this spin degrees of freedom, of course, but they predicted phenomenologically, no microscopics, phenomenologically, by tuning the bandwidth of a Chern insulator with different spins. Many new topological phases and gapless phases, just from the effective theory, but no macroscopic calculation. I wonder if you or anyone has studied, for example, if you introduce a spin degrees of freedom and change the bandwidth, you have ferromagnets, you have a gapped quantum liquid, etc.
I see. Yeah, that's interesting. Yeah, I didn't study that.
They propose a lot of different phases, but without any numerical justifications.
I see.
Okay. Any other questions from the audience?
Hello. I have a questions. Yeah.
Okay, good.
Okay, yes, thanks Prof. Liu for the talk. So from my understanding, you are proposing a way to realize fractional quantum Hall states on the lattice, right? And for example, the just magnetic lattice. So I'm wondering how much, using this framework, how much of the traditional FQH study we can take, we can transfer to this, because traditionally we write down model wave functions, right, and do things with the wave functions. So on the lattice, for example, do we have a ground state? Can you write down the ground state for this lattice blocking state, and can you show that it's mathematically connected to the Loveling? So how? Yeah. So.
Well, for the chain number 1 block band, some people have established the mapping to the conventional Landau level. So they map the Warnier states of chain number 1 bands to the Euro Landau lowest Landau level. Then they can write down a model wave function also on the lattice.
That is analogous to the Lovelings state.
Okay, so once you have that, you can take all the physics we have known and
Yeah,
another test.
once we have that, we can calculate the
Theoretically.
overlap between numerical ground states on lattices with lattice model wave functions. And we can find, okay, the overlap is very high, it's higher than 90%. Then we can further compare the ground states, the Lovelings fractional Chern insulators. But for high Chern number bands, there's no such mapping.
Yeah, so that's what my next question was going to be. So, so that's, is it a new phase or is it a?
Yeah, I think there are new phases, but the nature is unclear.
Okay. Do you know anything about its all the topological indices of these phases, and we can compare with it? Or are they remain to be studied?
Well, the whole conductance is known. For example, abelian states is just the Chern number state divided by the number of degeneracy, right?
Can you calculate the whole viscosity as well for the C equals to 2 or C equals to 3 fractional Chern insulated state?
That could be difficult, right? But maybe I can calculate the modular matrix.
Yeah, just by deforming it, huh?
Yeah, this needs further study.
Yeah, okay, thank you.
So maybe a related question. So am I right in saying that for C equals to 1, everything for the fractional Chern insulator can be understood in the context of fractional quantum Hall effect?
Yeah, I think so.
Okay. And then for C equals to 2, are there topological phases in C equals to 2 that are related to fractional quantum Hall effect?
In some special cases, yes, it can be related to bilayer fractional quantum Hall states.
Ah, I see, I see. Okay. But there are many of them that you can't, there are new topological phases in some sense.
Yeah.
Okay, that's interesting. Okay, good. Do we have any more questions? If not, I think we are running out of time as well. Again, I apologize for the beginning. Let's thank Liu Zhao again for the very nice talk.
Thank you.
Thank you very much. Liu Zhao, do you have a time for a quick chat after this?
Yeah.
Oh, okay. So, Tron, can you create a breakout room for me and Liu Zhao? Do you know how to do that? Ah, okay, great. Okay, thanks everyone.